film number 4 in this series of AD and DA converter films. And now we move into the AD converters. But first, let's look at some converter basics. And again, the AD converters are found here in the signal conditioning process, and they deliver data to, for example, a computer over here. The signal that we have is analog, like this blue line here. When we convert, we measure that voltage at specific intervals. So we measure it here, 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 and so on. And then we need to hold that voltage for a given time while we do the conversion to a digital value. So you have your waveform and you sample, hold it, sample, hold it, sample, hold it, sample, and hold. So you need something to a sample and hold circuit while the numerical value is calculated. And the sample and hold circuit looks like this. You have an op-amp, which is a so-called voltage follower. So the voltage you have here will be copied over here and copied over here as well. So the voltage over the capacitor will be copied over to the other side. However, the current that flows into the op-amp is 0, so there is no current flowing there, while there can be a current there. And not there, sorry, here. Now, the control pulses are the ones that tell us when to sample. And the V in is the voltage that we want to convert to a digital value. When the switch here is closed, so when the switch is closed like this, a good contact, the V in here is transformed over to the capacitor, building a charge in the capacitor. When the switch opens up again, the capacitor charge has nowhere to go. There's no current flowing there, no current flowing there. So the capacitor will hold its charge, which means that it will hold its voltage. So the voltage here will be measured over here, copied over here, and presented to the output here. When the voltage now changes to a new value, drops for example to here, the switch closes, the capacitor is given a new voltage value, which it will store when the switch opens up again. For AD converters, we have 4 measures of quality. First of all, the sampling frequency. How fast does it sample? How often does it sample? So that is basically the x-axis. How many of these dots do we have per time unit, per second? Quantization is the resolution, and that is the number of division lines here on the y-axis. And that is the number of bits. In the conversion. So if I have an 8-bit converter, I have 2 to the power of 8 levels, 256 levels. If I have a 16-bit converter, 2 to the power of 16, 64,000 roughly. So that is a number of levels. So the quantization is one quality measure for my AD and DA converters. Linearity is that equal voltage steps over the entire range. So let's look at 2 examples here on the y-axis. If I have poor linearity, maybe I have something like this. I have steps here, and the steps become wider. That's not very good. A better linearity would be if I had equal steps for all levels. You see here, this step here is much larger than the step here. And basically, I guess the steps here were supposed to be equal, but my handwriting wasn't very good. But the steps here are equal, so then I have good linearity. Stability means that you have the conversion you do one day will be the same as the conversion you do another day. So there is no drift on the input-output relation. Then you have good stability. But on the other hand, let's go back to the quantization and the sampling frequency. A better sampling frequency, a higher sampling frequency, means that we take more samples per second. And I guess that would be better to have as many samples as possible. Remember the Nyquist-Shannon theorem, which says that there's a link between the sampling frequency and the maximum frequency that you can keep and be able to recreate on the other side. Now, if I sample too rarely, then I will lose some information. But if I sample too often, I get too much data to process and to store and keep. The same thing with quantization. If I have poor quantization, means that the span of my analog signal here, the span with poor or low quantization, low bit level, will divide the span into too few levels. A better resolution, more bits, better resolution, and even better than that maybe. But then again, for each sample I will get more data to keep, store, calculate, and use. So there is a trade-off between the quality and the amount of data you can keep, store, and use.